In this video, we are looking at two historic dams. One of them is still here after a catastrophic flood that destroyed other dams. Inside are generators with unique controls. Hello, I'm Jason from Steam, Electricity, and Propulsion. Let's explore the history and machinery of the Dayton Hollow and Central Dam in Fergus Falls, Minnesota. The Dayton Hollow Dam was built by the Otter Tail Power Company in 1909, which was the company's first power plant. Today, it's still operating with one original generator and even a rare mechanical governor. We will come back to this in a bit, but first, let's see how this dam survived a flood the year it was built. The city of Fergus Falls built the City Electric Light Dam in 1908, but unknowingly built it on top of a natural spring. In September 1909, the dam collapsed. Operators escaped the powerhouse as the dam breached and ran along this path. Once they got into the city on horseback, they warned residents of the flood. The surge of water destroyed the original central dam. The flood continued south, straight towards the newly built Dayton Hollow Dam. The president of Otter Tail arrived at the Dayton Hollow Dam nearly 2 hours after the dam breach happened. He opened these floodgates to dump water down the spillway. This may have saved this historic powerhouse from destruction. Most tour videos will just talk about how this works. We're going to see what's actually going on inside. Parts of this system have been modified or replaced, but Dayton Hollow has operated for well over a century. The powerhouse originally had 3 horizontal units, but around 1929, this 520 kilowatt vertical unit replaced one of the originals. This is the newest generator on the Otter Tail River system, and the only one with its original mechanical governor. A motor drives an oil pump with a recirculating valve. Oil is stored at 190 psi in this compressed air tank. The recirculation valve closes intermittently to refill the tank. Now that we have a supply of high-pressure oil, let's look at how the governor works. The operator adjusts the gate position with this knob. When the main hydraulic piston moves, a link connected to the compensation mechanism moves this lever. This creates suction or pressure in an oil-filled dashpot. The oil pressure causes the spring-loaded lever to act against the pilot valve, slowing the response and preventing overcompensation. Oil slowly moves through an orifice, allowing the spring to return to its normal position. These fly balls are currently disconnected, but they would normally regulate the generator automatically with centrifugal force. A synchronous motor at the base ensures the fly balls change speed directly with the generator. As the balls move, they control the pilot valve. This generator runs at 225 RPM and has 32 poles. as 16 pairs of north and south electromagnets pass the stator at 3.75 times per second, 60 cycles of alternating current is generated. This is the turbine and wicket gate housing which the governor controls. Now let's look at the control panel to see the operating conditions and controls. Right now the generator is near full load, producing about 500 kilowatts. The power factor is close to unity, which means the excitation is set correctly. About 55 amps and 60 volts are sent through these slip rings and brushes on the top of the alternator to create the magnetic field. The ammeter is not reading accurately, but the actual current should be around 150 amps. This voltage gauge is scaled down to 120 volts, while the actual generator voltage is 2,400 volts. Behind the generators is a large cavern beneath the dam. Now we're going to see how a turbine works. A new turbine has been built for the central dam, and we'll come back to this in a bit. The central dam, also known as the Wright Dam, was built around 1922. It replaced an older dam built in 1871, which was destroyed during the 1909 broken down dam disaster. The central dam's generator is currently dismantled and not running, but we can still see inside the machine. Inside, there are large windows to let in lots of light. Unlike the other powerhouses on this river, there's a small office in the corner that was used by an operator before these dams were automatically controlled. I've climbed up a ladder to get a better view of the alternator's massive rotor. You can count 48 poles on the rotor. This generator would have run at 150 RPM, which is the same as at the Pisgah Dam. However, this generator is less powerful due to a shorter dam, with a maximum power output of 400 kilowatts. Looking down is where the turbine and wicket gates would be installed. The concrete is shaped like a volute casing to funnel water into the wicket gates. The old turbine was sent to a shop where a new duplicate was constructed. It has now arrived at the shop near the Hoot Lake power plant. This is a Francis turbine where water from the wicket gates hits the blades at about a 90-degree angle. Water flowing down hits these scoops and is directed in the opposite direction of the wicket gate flow. This is a sealing strip which is machined to 1/20th of an inch clearance from the casing. Here is the new wicket gate mechanism. The wicket gates and turbine will be installed in this pit. Water from the turbine will drain through this opening and back to the river. Here's a close-up of the control gauges. This one resembles the one at Pisgah Dam. These old dams have a lot of interesting machinery and history behind them. Let me know in the comments what you found most interesting. If you'd like to see more about power generation, check out my videos on the steam plant in Hibbing or the history of the Hoot Lake power plant here in Fergus Falls.